Hello everyone, in today's class we're going to explore about limits and continuity. So in the last session we saw this as an interval over which we calculate got smaller the secant slope approaching the tangent slope. The limit gives us a better language which we are going to discuss the idea of approaching. So if you remember in the last classes we're talking about that, hey, I am trying to find the tangent line for this point A. Our approach is to find a point B that getting very, very close to point A. In that case, the secant line for AB, we can consider that is very, very close to the tangent line of point A. So the limit of a function describes the behavior of the function when the variable is near but does not equal. So in a specific example is this one. If you see a graph, such as look like this one, at this point is a circle, that means the function is not defined. Y equals to fx is undefined at, let's say this is point A. At that point, but there's a limit because we can get very close to it on both sides to find the limit of the function. So we will discuss more about that in the later. Okay, so we can say the limit of the function fx as s approaching to a number, let's say c or a, since we're using a in here, when it approaching to a is, so remember that the function at x equals to a, which is f of a, is undefined because it's empty circle. That means it's undefined. However, the limit can be defined. Let's say the limit is equals to L, pointed at the point L. So we can say, hey, the limit is L, and we can write as the limit of the function fx as x approaching to a is equals to L. So the symbol of this arrow means approaches or gets very, very close to. So f of a is a single number that describes the behavior of fx at the point A, but the limit of fs is a single number that describe the behavior of the function near fx. Okay, so this idea is similar to what we had earlier for the b. Remember, limit, we're trying to describe the behavior of the function near to point A. So I'm going to write this down. So f of a is a single number that describe the behavior of fx at the point x equals to a, right? At that point, as we see on the graph. However, the limit as x approaching to a fx, the whole thing, is a single number that describe the behavior of fx near but not at the point s equals to a. So we are just getting close to a but not equals to, okay? Okay, so I'm going to show you a graph and then I'll tell you which one is limit, which one is the function itself. So you can distinguish the differences between these two guys. So here is the graph. Let's take a look at the value of f of a and the limit of x approaching to a. What do they equals to? So if you take a look, f of a, there's a solid dot. That means f of a is equals to 2, right? So I know that this is equals to 2. What about the limit as x approaching to a? Approaching to 2, sorry. Yeah, approaching to 1. I should say 1. 1. It's 1, 2, 3, 4. All right. So what happened? As they're approaching, the limit is getting close to what? 2. So this is 2. So now let's take a look at f of 2 equals to what? Well, f of 2, this is a empty circle, right? Let me use a red pen. This is a empty circle, so that means f of 2 is undefined. So now what about the limit as s approaching to 2? What's the behavior of the function when they're nearby 2? Well, if we take a look, I'm approaching to 2, I'm approaching to 2, so the function seems like it's very getting close to 3, right? So that means the limit as the function approaching to 2 is 3. Okay, so now the next one is f of 3. Now I'm going to use a different color of pen. F of 3 is in here, right? Well, f of 3, where's the solid dot? The solid dot is in here, right? So that means f of 3 is going to equal to 2. However, the limit as s approaches to 3, the function look like what? In here, approaching to this empty circle, which is the limit is equals to 1. So you need to remember that the limit is completely irrelevant to the value of the function, which is this one. They don't have to be the same. We only care about what happens to the function, the graph, for x really close to 3 but not equals to 3. Okay, so another one is 4. Well, f of 4 equals to this solid dot, which is 1. But what about the limit? The limit of the function as x approaching to 4, what happened? Well, if you look at the graph from the left to the right, the function seems, hey, approaching to 2. However, on this side, the function is approaching to 4. So that means in this situation, the function value does not close to a single number, because by the definition of limit is here, they're approaching to a single number. But in our graph in here, it's approaching to 2 numbers. One is approaching to 2, in here, the other is approaching to 4. So since they're not approaching to a single number, we can say, hey, the limit as x approaching to 4 does not exist. So usually I will write as D and E. That means doesn't exist. Okay. So another good example is here. Find the limit of this function as x approaching to 1, 2x squared minus x minus 1 over s minus 1. So we know that in the math that, hey, when x equals to 1, the denominator equals to 0, the function is going to be undefined. So now, what can we do? Can we just say, hey, the function doesn't have a limit as x approaching to 1? Well, we can try to use a table to test them. Remember, on this graph, how do you find the limit? Is as x approaching to that number as close as possible. So that means if we're making a table with s and fx. So if x equals to, we find a number close to 1, let's try 0.9. So the function, if you substitute 0.9, you will get 2.82. You can calculate that by calculator. Well, we can find a number even closer, such as 0.9998. Then fx is going to equal to 2.9996. And then we find another number, 0.999994, and then we substitute into the function, we will get, because as long as it's not 1, as close as possible, the function is still defined. So this is equal to 2.999998. So you may see a pattern right now. So as this number x approaching to 1, the fx is approaching to 3, right? So can we say the limit of x of the function as x approaches to 1 is equal to 3? Well, do you remember our last example? For as x approaching to 4, what happened? Well, the left side is different from the right side. They don't approach to a single number. They're approaching to 2 different numbers. So that means if you're using a table, you need to check the other side. So again, well, we can find 1.1. That's close to 1 on the right side, right? So the function is equal to 3.2. If I try 1.003, the function is 3.006. If I try 1.001, the function equals to 3.002. And if I'm trying another one, 1.00007, the function, when you substitute into the fx function, you will get this number. So as you can see, as s getting very close to 1 from the right side, the function is close to 3. So that means from these two tables, you can conclude that, hey, no matter from the right side or from the left side, s is close to 1, the value of fx are getting very close to 3. So we can get fx as close to 3. We want to take in s very close to 1. So now we can say the limit as s approaching to 1, the function equals to 3. Okay, the other way you can do it is using an algebra. So one way is using a table. The other way to do it is using algebra. So using an algebra, we could have found the same result by noting that, hey, the function equals to 2x squared minus x minus 1 over s minus 1. So now let's try to factor the function, see if we can get rid of the denominator. So when you factor it out, you should have 2s plus 1 times s minus 1 using AC method, and then s minus 1. And now, since they have common factor s minus 1, these can be crossed. Oops. So these, we have 2s plus 1. So 2s plus 1, what happened? Well, so that we have the limit as x approaching to 1, 2s minus s minus 1 over x minus 1 equals to the limit as x approaching to 1, 2s plus 1. Well, in 2s plus 1, as x getting close to 1, what happened to the function? The function is 2 times 1 plus 1 because it's defined at x equals to 1. So this is equal to 3. So that means the limit is still equals to 3. No matter which way you use. If you're using a table, you need to do it from the left side and the right side. If you're using algebra, you need to try to get rid of the denominator if it's possible. And then another way to do it is using a graph. Well, then we can use a GeoGebra to help us. I'm sorry, decimal. When you go to decimal.com, choose the graphing calculator, and then we type in x squared 2 times x squared minus x minus 1 divided by x minus 1. Oh, x minus 1. Sorry about that. And then now let's take a look what happened when x equals to 1. So the function is in here. So in decimal, they're not smart enough to notice that, hey, s equals to 1 is undefined. But you can tell in the graph from the left to the right, it should be more like this on the real graph. When they're approaching to it, it should be a circle. And then you know that, hey, when you're getting close to it, the function, the limit of the function as x approaching to 1 equals to 3. Okay, so now let's go back to our early example, the graph example. As you can see, there's two limits for 4, right? One is from the left, the other is from the right. So we call it one-sided limit. So one is called left limit. So what is left limit? So that means as x approaching to our destiny point, could be point A, point B, point C, 1, 2, 3, 4, 5. Let's say as x approaching to some number A, of fx is L if the value of fx gets as close to L as we want when x is very close to the left of C, which is on the left side. So such as, I'm going to draw the graph again. So you have a graph look like that. So this is our point. Oh, let's use point A. So what is left limit? Left limit is when the graph approaching to a from the left side, to the left side of a. That's the left limit. So we write it as the limit as x approaching to a to the left, which is there's a negative sign on top of a, fx equals to a number. Let's say this is number b. Okay, so what is the right limit? So the right limit have the similar idea, which is you approaching it to the right side of a, and let's say this is equals to c. So we can say the right side limit returned with x approaching to a plus. This is a minus if it's left side. And then we can write as the limit as x approaching to the right side of a equals to c, because that's equals to c. So what happens if you see something like that? This is our point A, and let's say this is L. Oh. So that means the right side limit of A, the left side is the left side. The left side limit of A is equal to L. Also, the right side limit of A also equals to L, because they are all approaching to L, right? No matter from the left or right. So that means sometimes two side limits are the same, sometimes they are not the same. So they have two situations. Okay, so now let's take a look at an example. Okay, so now let's take a look at this example. Let's examine fx, and then as s, and then the limit as s approaching to some number from the left side and the right side, and see what happens. So let's say when fx equals to 0, the function equals to what? Which one is defined? Equals to 1, right? Because that's the solid dot. So as s approaching to the left limit of 0, so that means the function is coming from the left side to 0. That is equal to what? Well, the left side limit at x equals to 0 is equal to 1. But what about the right side? So the right side limit as x approaching to 0, look at here. This is approaching to 2. Okay, they're different. Now can you try x equals to 1 by yourself? I'm going to use a yellow pen. So f equals to 1, the function is defined in here, right? Equals to 1. What about the left limit? This is equal to what? From the left side, when they approaching to 1, the function seems getting close to 2. What about the right side limit? As the function approaching to that, this is equals to also 2. So that means when x equals to 2, the limit is equals to the left side limit equals to the right side limit. Okay. A second one is when f of 2 equals to what? F of 2 is here equals to -1 I'm sorry, this should be negative 1. And then the left side limit as x approaching to 2 is equals to also 1. And the right side limit, negative 1, sorry. The limit to the right side of the function also equals to negative 1. Okay, now let's take a look at 3. So f of 3 equals to, the function is defined here, f of 3 equals to 2. And then as the function approaching to 3 from the left side, which is this way, the limit of the function is negative 1, but when the function approaching to the right side, the limit of the function equals to 1. So in this case, the left side function is not equals to the right side function. So when we determine a function, why do I need to know the left side and the right side? The function only exists only if the left side function equals to the right side function. I'm sorry, I say here's, let me starting with the left first. In that case, we will say, hey, the function exists. Otherwise, they won't exist if they go into two different directions, like what we have in here. Okay, so the last part of this chapter is continuity. So the definition of continuity at a point is when the function is continuous if only if the value of the function is equal to the limit of the function. So what does that mean? Well, now let's take a look at our previous example. So let's take a look at the first one. So the first one, if you want to have a continuity, first of all, you need to have a limit. So in the first example, the left limit doesn't equal to the right limit. So that means the limit as x approaching to 0 does not exist. So there's no limit, so we don't need to worry about continuity. So what about x equals to 2? Well, when x approaching to the left side and right side of 1, the limit of the left side limit of the function and the right side limit of the function, they're equal to 2. So that means the limit as x approaching to 1 exists, which also equals to 2. However, the value of the function is negative 1, but the limit of the function is 2. These two is not equal. That means they're not continuous. Now let's look at x equals to 2. The first thing we want to examine is if they have limit. Well, since the left limit and the right limit, they're equal, then I can conclude that, hey, the limit as x approaching to 2 is equal to negative 1. Also, the value f of 2 equals to negative 1, which is equal to the limit approaching to 2, as the function approaching to 2, it also equals to negative 1. So that means the function at x equals to 2 is continuous. Okay, last one. Again, the left limit and the right limit, they are not equal. So that means the limit as x approaching to 3 doesn't exist. If they don't exist, we don't need to discuss about the continuities. Okay, let's give some examples about continuities. So evaluate using continuity if it's possible. So the first example would be the limit as approaching to 2 x cubed minus 4x. So the given function is polynomial and it's defined for all values including x equals to 2. So we can find the limit by direct substitution, such as the limit x equals to 2, we substitute 2 into the function, which is equals to 0. So that means the limit at x equals to 2 is 0. Okay, and another example would be the limit x approaching to 2, x minus 4, and x plus 3. Well, the given function is a rational function. It is not defined at x equals to negative 3 because when x equals to negative 3, the denominator equals to 0. But we are taking the limit as x approaches to 2, so we don't need to worry about the undefined at negative 3. And the function is defined at that point, which is great. If they define, that means we can just substitute the function x equals 2 into the function to find the limit. Okay, a last example would be the limit as x approaching to 2, x minus 4, and then x minus 2. So you need to be careful in here because the function is not defined at x equals to 2. So if they're not defined, so that means at this part is not continuous at x equals to 2, so we cannot use a direct substitution. Okay, that's it. So let me know if you have other questions.